Okay, welcome everyone. This is the Digital Design and Computer Architecture lecture. My name is Frank. I'm not Onur Mutlu, I'm not a professor. Now you're asking, yeah, we paid for this course, we wanted a real professor to come, why are you here? I hope I'll be an adequate replacement. Every now and then during the lecture, I'll be taking over a few lectures. I'm from electrical engineering. Bad people, they eat it, right? I mean, I'm perfectly aware that if you wanted to study electrical engineering, you would have gone to electrical engineering. And now you said, hey, I want to be cool, I want to be in the computer science, which is very nice and good. And why does this electrical engineering person come and bother us? In the lecture, we are trying to give you also an overview. No, don't worry, I'll do the shishing, don't worry, don't worry. I'll have it under control, I'll scream louder, don't worry. I'm not doing a good job if people are keeping talking, right? So it's my responsibility. Anyway, after this brief introduction, let's start with the not so nice things, the assignments, what you have to do. So we'll be covering combinational logic. We started a little bit late because yesterday we were talking about the exercises. And next week we are going to quickly move from the simple combinational logics into hardware description languages. And these are the chapters that we will be covering. I mean, we start today with combinational logics, and next week it will be hardware description languages and even in sequential logic. And by the end of the next week, make sure that you have covered these parts of your textbooks. So, I'm here, so it's actually a good thing to discuss this a little bit, a note on hardware versus software. It looks as if this lecture actually doesn't belong into this curriculum, right? Computer science. And if you fast forward, if you're watching this on YouTube, if you fast forward half an hour, you'll see transistors and gates and things like that. So it might seem it's a little bit only computer hardware, but there is actually a lot of benefits to be gained to learn, let's say, the highlights of what the electrical engineering students are learning about designing computers, making them. So if you understand what is lying underneath, that will give you chance to make better choices when you're developing your software. You can also design better hardware if you understand the software. So if you understand both of them, we will be able to do much better computing systems. And this is also, although we are joking that computer science, electrical engineering, this is also one of the key areas that collaborations are going on between computer scientists, electrical engineering, material scientists to build better systems. So this course covers actually the hardware-software interface and the microarchitecture. How do we build and design systems that we use for computing? And the special focus is on how are the choices that we have making the hardware affect the performance in software, and vice versa. What kind of problems do software people cause for the hardware people? Poor hardware people. Okay, so in the introduction lecture, Onur was talking about the four mysteries. And if you remember, anybody remember these things? Meltdown spectra? Great. And then the others, row hammer, memory performance attacks, memories forget. What was the key idea behind them? Why did Onur talk about that? I get the chance to throw this, come on. 300 plus people. Oh, challenge accepted. Well, you have to help me. I'll throw it halfway and you'll throw it further. Oh, it wasn't bad. You have to open it. But I hear you. He said hello. Yeah, so in case it didn't go into the recording, all these four have in common that the reason there was a problem, there was an attack, was not because there was anything wrong with the software, but we were able to exploit properties of the hardware that people assumed to function in one way. And when you look in detail, you realize they are actually doing something else, and people were able to exploit it, which was a problem. It's not only for exploits, it's sometimes also the same realization leads to you to make better decisions about how to take advantage of things and how to make better systems. So there was one more assignment. Why are we studying computer architecture and future of computing architectures? This one, I heard, was already announced on the Moodle. There's a required assignment. It's not my inaugural lecture, it's honors. And it gives you 1% extra credit, which is, yay, no. No, it's not working, I know. Okay, okay. So before we go into the future of computer architecture, and I know you all want to see the cool architectures and the big things, we have to start at the fundamentals. And it is not by choice. These lectures always have parts which are considered to be slightly more boring, because people have to talk about fundamentals, and they look very simple, and you say, why am I hearing about this? It's so simple, let's get to the interesting stuff. Unfortunately, if we do not understand the basics, we will have problems with the further topics. So we have to go over this. And it is also important to understand how we came at the decisions we came today. If you open your newest cell phone and dive and look into it, you will see a certain architecture. We didn't arrive at this because in year 2019, July, an engineer sat down and designed it that way. There is maybe 30, 40 years of development that there were decisions being made one after another, which led us to the hardware that we have today. And over the years, we had seen and evaluated different architectures. We saw what they do well, we saw what they don't do well, and made decisions. These things are not static. They change over time. When the requirements change, when the technological capabilities change, get better, we may be able to make and take advantage of some of the things that we ignored previously. So let's come back to our fundamental concepts. So the first thing is, what is a computer? We are computer scientists, we care about it, and you can make the argument that we have three key components. Somewhere we compute, then we communicate, and then we have storage and memory. And it looked like this in the late 40s. That's von Neumann standing in front of his architecture. And you can abstract it very simple like this. There's somewhere where we are storing the data. It has a larger storage system, maybe a disk, a memory system, and somehow the data here is communicated to a unit that does the real work, that adds numbers, XORs them, does some fantastic things. And maybe today you could equate them that there's a processor here, there's a DRAM array here. This is probably, does anybody remember this thing? Okay, these are rotating magnetic disks that were called hard disks. No, not, yeah, we are getting older. I recently realized that for most of you, it doesn't make any sense. Next to the save, there's an icon, which is a floppy disk. And a lot of people are asking me, why is this icon there? I say, we used to, I'm old. Okay, so we will cover actually all three components. We will talk about processing, and the processing we will realize that it will be divided into two main parts. There is the one that does the real work. We call that a data path. So data enters from one side, gets processed nicely, and exits on the other side. And something controls the order of how this data is processed, operated on. And that's the control or sequencing part, which says, let's first take these two numbers, add them, multiply them, then subtract them, then write them back to this part. We will see that memory, program, and data are going to be an important part of the equation, because a lot of people concentrate on this part, saying, yeah, we need to multiply faster, make things faster. But we will see that a lot of the issues actually come because we cannot feed these units with enough data or the right data at the right moment. And I/O always is an important thing because, well, if there is no input-output to the system, there is this box, it's doing fantastic computations, nobody knows about it, okay? It's been here, sitting here for 2 hours, it did all the nice machine learning algorithms and did a lot of classifications. We don't know about it. It's practically useless. So, let's again come to the hierarchy, and this is one of our key aspects, how we handle complexity, right? We discussed this in the first lecture. If you look at the systems we are building today, your cell phones, high-performance computing centers, and if you say, okay, I'm going to start from the top left edge and design everything, we are hopelessly overwhelmed with what we do. So we are able to abstract things on multiple levels, and that allows us to concentrate and look only at that level, solve the problems, and we know that, okay, this is this level, and then the next level, the next level, next level. What classically in computer architecture, they are just looking at the software-hardware interface, which tells the software how the hardware looks like, and here we are implementing the instruction set architecture into gates, and that's it. But what we are looking at is a more expanded view where we are going from algorithms all the way to devices. At some point we are stopping, so we are not going all the way down to physics, but we will cover all aspects that will allow us to make computers work. And the good news is, at the end of the lecture, in the exercises, you'll be able to design you'll be able to design a processor that executes your programs on the systems that we have. There's one. It's correct, right? Okay. And today we are going to cover combinational logic design. We will start with that. And that was the way, or we will see how we were looking at the problems in my time, let's say 20, 30 years ago. But then, fortunately, we will, starting next week, realize that there are actually more practical ways, machine-understandable ways of describing hardware and telling how to put things together. That will be the hardware description language. Once we have mastered this a little bit, so we are able to work with it, we will go to the sequential logic design, and then will come timing, then we are looking at the processors, assembly programming. We are not done. Then we will say, now that we know what a processor is, how can we implement it? There will be single cycle, multi-cycle, pipelining, out-of-order execution, all in this lecture, mind you. Nobody's excited at all. You're just looking at it and saying, oh my God, it will be difficult studying for the exam. And other processing paradigms. And I'll leave it at that, just a second, it didn't. So, this is for setting the stage. We have to start from somewhere, and we are going to start from the very, very bottom, combinational logic circuits and design. So today's learning goal is to understand what are the modern building blocks of computers. And the simplest building block is transistors. We will talk about that. Don't worry, we are not going to go into any of the annoying details about transistors. If you are studying in electrical engineering, this thing would ruin your life. You'll be learning about the equations, formulas, draw graphs, and things. We are not going to do that. We are going to simplify it a lot. Out of the transistors, we don't actually care so much about them, but we want to go to logic gates, doing very important, simple Boolean operations, like inverting. And then we will start with an algebra. This is actually a kind of we learn how to build logic gates. Now we have these fantastic things that can do something. We realize we can solve problems with it, but we don't know how. So the Boolean algebra will help us, gives us a theory how to reason with them, how to think of them. If you have a problem, we can use Boolean algebra to express it. And then these gates allow us to make things that actually work. And the first thing that we will do are combinational circuits. And the combinational circuits are the nicest circuits available. They have a set of inputs. You provide the inputs. And the moment the inputs are there, the outputs will be directly determined by the available inputs, which is very nice. The slightly more capricious version is the sequential circuits, which not only take the current inputs, but it has a memory. It also remembers what you did previously, which is kind of annoying. And this is why we are going to separate them and first look at the simpler case where we are only concerned about the present inputs, which directly give the outputs. And we are going to use the Boolean algebra to help us build the circuits and also minimize them if possible. I'm going to come into why we care about minimizing, hopefully by the end of the lecture. So here, this is a picture of a very small, this is a 5-cent piece here, microprocessor. The guy is sitting here, there's a bit of memory. This is a small SD card connector and a small thing. It's tiny, tiny, tiny. And somewhere there, I am pointing at it, there's a microprocessor. Now, in your lectures, in your exercises, you are using these FPGAs. We started the exercises? Who was in the exercise? You had this board, right? Isn't it great? You can, the most important thing is here. We have to make sure that if you are building a bomb that the hero diffuses, that you program these perfectly. So these are FPGAs, and technically this is a bigger board, but what is doing the work here is this middle part, this similar looking thing. And at ETH, you can also design your own ASICS. If you are part of VLSI 123, it's a lecture series in electrical engineering, you can design your own circuit. So these things are things that you buy. This one is customized. And a student of us, it's a RISC-V processor that made it. Now, the problem is, they all look exactly the same. Now, let's take a look at that. This is like this black kefeli. The other one, similar. The other one, quite similar. So they all look, they look very much the same. Do you agree? Same? So what's in them? Why do we care? So we know that these are the common building block of computers. This somehow is reconfigurable. And this thing is that some electrical engineers make and show off a lot for some reason. The interesting part is that the program development time. So if you have a program that you want to burn onto this microprocessor, microcontroller, it takes maybe minutes. You will argue with me about this. So if you have an exercise, you want to program your FPGA, it may take days. And this thing takes months to actually finish and say, yes, I have a new chip. So why do you care? Because if you look at the performance, this is by far the most you can get, because you can customize every little detail of it. This one is, takes longer to program, has more performance, and this one is easier to program, but, doesn't have as much performance as the others. So what are they good for? Well, you can use a microcontroller everywhere. Do you know how much one costs? Like a small 32-bit microcontroller, how much would I buy them for? $2. $2. Who said $2? Anyone who says more, less? Yeah? 15 cents. Okay? It's cents. Millicents. Well, isn't it scary? Somebody made these microcontrollers and they sell for nothing. If you have any friends going to electrical engineering, and you can say, you guys, your work, it's not worth anything. $2, 15 cents. It's true, it's true. And it's scary, it is something you can put literally everywhere. And so this is good because it's simple to use. Anybody who has basic programming skills and a development environment for that particular microcontroller can program it. So you see it everywhere. These ones are kind of harder. They are good for prototyping. They are good for small volumes. So if you're not selling this to millions of customers, this is good. And this one is for mass production, max performance. You need to sell millions to be able to cover the cost that you put into this. First of all, it takes a lot of time to design it. It's expensive designing cost. So you have to make sure that you get something back. So how do you program this? Well, this one is an executable file. You use C, C++, Java, Scala, whatever your favorite language is. And Intel, ARM, and AMD are the main companies that you might know about this. For this thing, we create a bit file somehow. It's like a program. It's uploaded. It configures internally what the FPGA does. We are using things called Verilog VHDL, and the main companies, Xilinx, Altera, Lattice. And this one, we are not even programming on the run. They are, we are sending blueprints, how they are manufactured to a company. They manufacture it. Still, mostly it is designed Verilog VHDL, and these are the companies that you might have heard of, TSMC, ST, Microelectronics, Global Foundries. So what we are going to do is we want to learn how these things work. This is our goal. But to learn this, we are going to use this because it's flexible, we can program it, we will be able to make newer versions of custom versions of the processor ourselves, and we'll be using these languages here to be able to do this. So we want to learn how these work using this thing, using this language. Simple enough. Yay! Okay, so much introduction, and the lecture is not started yet. So let's start from the very, very simple block, transistors. So in order to have a modern computer, you need to put a number of these transistors together. We are not going to go too much into detail. I'll try to sketch something here, just how they are built. Just to give you an idea, Intel's Pentium 4 microprocessor first offered in sale in 2000. Who's born here before 2000? Oh, excellent. So, this is your processor. Who's born after 2000? Ouch. It was made up more than 42 million MOS transistors. So we took 42 million of them. So this is, I don't know, roughly the size of Spain, or what is it, 6 times Switzerland. For every citizen in Switzerland, we had 6 transistors come together in a chip, and that ended up being a processor. And right now, well, not right now, but in 2016, only 16 years later, the Intel's i7 has 3.2 billion MOS transistors. This is roughly 1 transistor for every 2 persons or every 3 person on Earth. It's a massive jump. And what's even scarier for me is that currently in 19, 20, a student doing a semester master thesis in our institute can do a chip with 40 million transistors within 3 to 4 months, which is absolutely crazy. So in this lecture, we are going to look at how this transistor, whatever this thing is, we have to have billions of them to make it work, right? How it works and how we start with this thing. And we want to see how it works as a logic element. And if you remember our abstraction levels, we are going to look at the devices, which is at the very, very low level of what we are going to cover. So without further ado, let's start with the MOS transistors. But before we start, I'll have to... transistors work on electrical signals. Electrical signals are very practical. This is why we end up using them. And if you deal with electricity, there are a couple of simple properties of materials. So the first thing is conductors. Something very exciting. Anybody, any idea what does a conductor do? Or do you know any conductors? Copper. Is there a better conductor than copper? Okay, we have copper, we have gold. Is there a better conductor than gold? Yes. Silver. Which is correct, not argon. Okay, and then if you have conductors, they conduct electricity, right? You need to, if you have electrons on one part, you want to transfer it somewhere, we need a conductor, big deal. And what we also need is we need to isolate different conductors from each other. So we have insulators. Any ideas about insulators? No? No? Yeah? Rubber. Excellent. Something else? Ceramics. There will be a lot of materials that don't conduct. Yeah. Vacuum is very good. Air is also good. Let's have vacuum. Air. I'm going to add one more. Glass. Okay, so these are the very, very simple elementary things. But then there is one more material that is very interesting for us. These are semiconductors. So they wanted to be conductors, but they didn't manage it, so they are semiconductors. I'll spare you the agony. Silicium is one, germanium, or there could be even combinations of these things. Now, these are very interesting materials. Anybody know why? Why do I care so much about them? Yeah? Yeah, it's close. There is a good property, but you are close to it, yes?
By changing the structure of the, for example, silicon, what we can do is when we introduce certain additional elements, we can make them very good conductors.
Yeah, well, you are almost perfectly right. But the important thing is, semiconductors on their own are like electrically completely neutral. They don't tend to go one way, or they are not positive or negative. So what your colleague said is exactly true. Their biggest property is they are so nicely pure, if you can make them pure. You know, you have to make a structure that is only silicon atoms, and they are lined up nicely in a crystalline structure. Then this thing is perfectly neutral. And then you can make them dirty. You can add components, you can add some boron, you can add some phosphorus, and by that you change their electrical properties. You can make them slightly N, negative, you can make them slightly positive by the amount of impurities that you mix into it. It lets you engineer regions on a small scale that have different electrical properties. This is the great news about it. Silicon on its own is, let's say, less interesting. The interesting part is that you can engineer it. So this is the part that makes life fun. Okay, so lost my slides. Yeah, so we want to make a MOS transistor, and we will combine metal, which is a conductor, an insulator, oxide. I mean, glass is an oxide, silicon dioxide is glass, and the semiconductors together. And from the names, MOS, you say we have a MOS transistor. Ta-da! And this is how the thing looks like. It's slightly ugly. I'm just going to make life of the person filming this a living hell. Okay, so let's just start from here. So this is the surface of your chip. I'm just going to redraw this really quickly. Famous slice. Okay, so what you have here is a substrate that is semiconductor. And what you can actually do, we will engineer one part of this blackish looking thing. We are going to change its doping to N. So we say, hop, this region here is going to be N-doped. And this region here is going to have this stronger doping. So this is a semiconductor, and this is a part that we engineered. We start with a slightly, let's say, P region, and inside it we manufacture, and we say here we are putting some impurities, and we create these regions, these two parts. Then we cover, between them, we cover this part here with an oxide. We don't want any current flowing through here. So this is the oxide. So in this graph, we are looking at this tiny thing here. And on top of this, we need to make some connections. So there's a special connection that we have. The connection that is on top of the oxide is what we call the gate. So I'm drawing this part here. And then somehow these regions also need a connection, and I'm using a conductor. So that it can be connected further. In this graph, we are looking at these two towers. Frank, what are you doing? So, if you can bear with me, so this is a side view. We are looking at the transistor from the side. If we were to look at it from the top, so I'm drawing the same thing here, what we see is that we have this region, so this is this region. And so this is the gate, the red part. These are the things. You are asking, where is the blue part? Well, the blue part comes from the top and makes a nice connection. So we continue. So this is the thing seen from the top. If you want, let's put one more detail. We call this the width of the transistor, and we call this the length of the transistor. Okay, why do I care? Well, if you would do semiconductor device physics, and we will talk about that it works like a switch, there's a current flowing, who cares? Part of the formula has this W over L as a multiplier. There is a bunch of things which we are never going to talk about. But you know what's really great? If you want twice the amount of current, what do you have to do? Yeah, either this or this, right? We have to change this ratio. If you make the transistor twice as large, it draws twice as much as current. It's twice as fast. It's gorgeous. I mean, this is all you need to remember. Frank, I'm still not buying into this electrical engineering thing. I see. It is interesting to remember because there is a relationship between if you want something to be fast, you make it larger, means that it occupies more area when you look at from the top. So if I were to put on this blackboard here, I can maybe squeeze in 8 of these guys. If I made them double as large, I could only squeeze in 4 of them. Huh? So that's the entire story that we are looking at. Now, we are going to come to the more fun things. I think Onur is going to kill me that I drew these things. Okay. I'm out of breath, sorry. So, the question that everybody is asking themselves, why is this useful at all? Well, we can combine many of these. How many? Yeah? 1 billion, yeah? You know, just take 1 billion of these things, put them side by side, and wonderful things will happen. And we are not going to talk about the electrical properties. You know, start with here, there are evil things after this, you know. We're not looking at this. We just want to understand what is happening. And so life is a little bit complicated. We have two different types of MOS transistors. We call them an N-type or a P-type. Now, the N-type and P-type differ because this region we engineer to be N, or if we engineer this region to be P, we call them P-type. They are complementary to each other, so one works one way, the other one works just the other way around. And the way to identify them is they have three connections. They have a drain, a source, and a gate that controls the flow of current in between them. So if you are looking here, it doesn't matter. It's a symmetric structure. You can say this is a drain, this is the source, and this is the gate. And if you were to draw it, I have to rotate it then 90 degrees so that, you know, we are matching this drawing. And if you were to draw a P-type transistor, well, the only difference is we say, you know, to differentiate the two, I'm putting a little circle there to let you know that we are talking about the complementary type. And notice that I was talking about semiconductors being cool. You know, you can engineer these regions. You can have your big chip, and any part of it you can say, let me make this N. Let me make this region P. I can define a small region and say, this 5 micrometers by 2 micrometers will be of type N, meaning that I am building an NMOS there. Or you say, this region I will make P, and I will make a PMOS there, which doesn't sound very exciting until we see that they are actually useful. Who believes me? Yeah, I guess so. I wouldn't believe myself. Okay. So how does a transistor work? What is this being done here? So if you want to visualize it, you can consider this entire structure, this structure between here and here, as a switch. By controlling the voltage on the gate, or by pressing on the gate if you want, you can control whether or not current will flow in between. So if you have a power supply, and then you have me, and there's this wall switch. If the transistor is open, not connected, the light will not turn. So in order for the lamp to glow, or me to get an electrical shock, the electrons must find a way to flow. And we need to close the circuit. So by controlling this switch, I can either light this thing up, or when I open it, no current flows and the thing stays dark. And now everyone says, yeah, no. I appreciate that your patience, you know, you're still saying he will probably come to a point, right? Okay. So the beauty is, actually, you can use this transistor, and in digital circuits we use it mainly as a switch. In electrical engineering, there are also other uses of a transistor as an amplifier and whatever. Forget even I said that. We are going to use them as switches. We can turn them on and off as we want using electrical signals by controlling the voltage on the gate. And, sorry. So this is now, once again, our transistor. Here is the gate. This is the thing that controls everything. So if the gate of an N-type transistor is supplied with a high voltage, like 220 volts, and then there is the connection between drain and source is closed. So there is a current flowing. Now, let's not go too much into the detail. Depending on whatever technology we are using, this voltage could be something between whatever, 0.3, 0.5 to 50 volts. Most commonly these days in modern transistors, you use something around 1.2 volt. But let's just keep it easy in the examples. Why not? Let's use 3 volts. Okay? We just need 2 reasons. And so if I supply here 3 volts, this switch is closed. If it is 0 volts, this switch is open. That looks like a very, very practical circuit. Now that I have my switch replaced with a transistor, if there is 0 volt applied to it, 0 volt means the switch is open. The transistor is not conducting, therefore there is no light. And now I get upset, and I press, somehow give 3 volts. From my pocket, I take out 3 volts, put it to the gate, and the light turns on. If you want, we can simplify this with such a notation. Notice that a power supply always will have a return path. So there is a difference between here and here of 3 volts. When we draw schematics, we usually do not always draw this power supply. We say this is the high voltage, this is the low voltage. So there is, between this point and this point, there is 3 volts, if you will. Okay? Silence. Okay. Now, P-type transistor, now the N-type is the easy one. P-type is exactly the same, but the dual. What do you mean? So in the N-type, the circuit is closed when the gate is supplied with 3 volts. And in the P-type, well, the circuit is closed when the gate is supplied with 0 volts. Just the opposite. Okay. So far, so good. So now let's try to go one level up. We know what a transistor is. We have a switch. And in this very hypothetical situation, there's a bulb lighting and not lighting. And so we know how one works. Now we covered the devices. Now let's try to make sense of it and go one level up. Can we do something useful out of this strangely, turning on and off things? So we will start with a very basic logic gate, the most basic thing that we can think of. And we will see that we can implement simple Boolean functions out of circuits that are constructed out of these. So we will need 2, 4, 6, 10, 20 of those combined to make a logic function. And then we will realize that if I have logic functions, I can make more complex functions out of them. I can store data, I can add things, I can make adders, multipliers, CPUs, and other things, and then 2 billion of them come together, and we have a gorgeous microprocessor. So I will come to this. You could technically, when we first started doing things, we only used one of them. We just used either N-type or P-type transistors. The big breakthrough came in around 1970s. Anybody remember those nice times? No. In the 1970s, they realized that you can combine both of them together because they complement each other. When one is working, the other one is not. And when the other one is working, the first one is not working. So they work in it's either me or you kind of fashion. That's why it's called CMOS, complementary metal oxide semiconductor. And it combines, as I said, both NMOS and PMOS transistors together. And it's the simplest structure that you can imagine. It looks like this. So this is, again, my power supply. If you need to imagine there is a power supply connected externally like this. So I have one PMOS and then one NMOS transistor connected like this. These two things are connected together. These two things are connected together, and somehow I call one of them input and output. Now notice that this is P-type, this is N-type. What does this strange thing do? Well, let's see. That's me being very curious. And I have this, and I say, okay, I can do 2 things. I can either put 0 volts or 3 volts. Now let's put 0 volts. When you put 0 volts, what happens to the bottom guy, the NMOS? Anybody remember? Who says on? Who says off? Great. So this guy is off. What about this thing? Who says on? Excellent. So it looks like this. And if you are solving basic electrical equations, you see that if this is closed, and at the top we had 3 volts, if this is closed, then this point will also be 3 volts. And this part will be open. Yay. Let me just finish. So this P-type transistor managed to take our output and connect it, pull the output up to the higher point. Now if I am again there and I'm curious and I apply 3 volts, now this transistor will be on, this transistor will be off, like this. Now all of a sudden the output is connected to the lower voltage level, 0 volts, and here we have an open circuit. So the NMOS was trying to pull the output down. Okay, and so these things together is what we call a NOT gate. Something very exciting. It's a negative gate, You give him 0, he says 3. You say 3, he says 0. Completely disagreeable gate. And, it's also arbitrary how you interpret these things. In digital circuits, we have 2 different states. One is 3 volts, one is 0 volts, for example. And we can assign them a binary value. We can say, hey, 0 volt is binary 0, 3 volt is binary 1. Why not? Could be also the other way around. You'll just make your life difficult. And this is what happens. So if A is now a binary value 0 and 1, P's are on and off, Y is 0. And all of a sudden you see that, hey, if I take A as a Boolean variable and Y is a Boolean variable, this thing actually inverts the input. We have what we call an inverter, and it satisfies this truth table. Now, with this wonderful revelation, we take a break, come back refreshed at 1:15. Thanks a lot. Okay. 1 more hour before the weekend. Yay. Okay. So, after all these adventurous things about the transistors, we are finally coming to a thing that sort of kind of makes sense. We have this 2 transistor affair, and we can do a wonderful gate, a NOT gate, negation. And we discussed that it actually, we can symbolize this thing. So we know that internally out of transistors you build it this way. But we abbreviate this function and we call it a NOT gate or an inverter. It has 1 input, 1 output, as boring as it can be. And if A is 0, Y is 1. If A is 1, Y is 0. Great thing to have in your arsenal. So, well, if you want to do something useful, let's better do something that does a little bit more than just saying no. So, let's start with this thing, and for a moment, please accept this. I somehow connected them in this funny constellation. You could make an argument saying, Frank, why are these 2 NMOSes like this and the PMOSes like this? Why there are 2 inputs? Let's just investigate what is happening. It's just, I had a spare time, 15 minutes break. I combined them in different ways, and I realized something very interesting. Because this is me, once again, and I have 2 inputs now, not 1. And I somehow connected these. These 2 are in series, these 2 are in parallel. This guy here and this guy here share the same input. And this PMOS here and this NMOS here shares the same input. Somehow I call them A and B. And let's see what is going to happen here just out of the experiment. And I don't know why Honor is always making me like this angry person. So there is like inspiration comes, strikes, or I'm being struck by lightning. And I realize that if I have 2 different inputs, well, each one can be 0 and 1. So I have a total of 4 different cases. So both A and B can be 0, A and B, A0, B1, A1, B0, both of them 1. And I can actually play through the, and simulate this thing through and see what is going to happen. So I have here 2 PMOS transistors and 2 NMOS transistors. And we discussed this a little bit, and we said the PMOS transistors are the ones that are used to take the output and connect it to the high voltage. And the NMOS transistors are the complements. They try to pull the output down to 0. So if the output is going up, the PMOS transistors are somehow winning the game. And if the output is going down, the NMOS transistors are winning. Does that make sort of sense? No. Give me a few more minutes, okay? It will make sense. Or I'll lose my job. Okay. So let's start with the case. A is 0, B is 0. If they are both 0, we know that these PMOSs are conducting. If they are conducting, and these guys are open, it means that the output is directly connected to the top. Yes? Yeah, good. So we have A0, B0, and since all of them, these two are pulling up, we have the output at 1. Now we can go through and we can realize, actually, they both don't have to do the work. If one of them is 0, it's enough, right? Because it doesn't matter if both of them are closed. If only one of them is closed, this 3 volt will be connected to this output here. So both the case where A is 0 or B is 0, will also make the output go to 1. In fact, the only case where the output will go to 0 is if both N1 and N2 are conducting, and that only happens if A is 1 and B is 1. And sure enough, if we do this, both PMOS transistors are off, and these guys are on, and the output goes to 0. Now, something has to be said here. We organize this in a special way. Anything that is serial here is parallel here, so there is a duality somehow involved in it. And we had to make sure that for a given input combination, it's either the PMOS transistors pulling it up or the NMOS transistors pulling it down. There are rules, there are some tricks to make sure that no matter what you do, you can construct a logic gate that somehow makes this function. We are not going to go too much into details of this because this is what the poor electrical engineers also have to do something, so we'll leave it to them. And now we have a truth table, and we look at it, and we say, hey, I mean, this looks like a, A0, B0 is 1, 0, 1, 1, 1, 1. And we realize, well, this looks like a function, and I could write it down like this. So it is A and B not, right? So if both A and B are 1, we get a 0. If A and B are, or if either A or B is 0, the output is 1. It's a kind of a interesting thing. So it's like a AND gate, but we are inverting the output. This is a truth table. Anybody, actually, you should have seen some Boolean algebra, right? Yes. NAND gate. Do you know what the property of NAND gate is? Yes? No? What's interesting about the NAND gate? Yeah?
You can build all other gates using NAND gates.
Exactly. So the NAND gate is the one gate you need for realizing all Boolean operations. You have this thing, you can build anything. End of the story. Thank you very much for listening to. No. But technically this would have been enough. So the people who are making 1 transistor and 2 transistors, whatever, they said, 4 transistors, I have an AND gate, and yee-hoo, I can build everything. Now, for your normal operations and work, the way humans think, the NAND is kind of like showing things this way. You want to build an AND gate, right? Makes a lot of sense. And let's try to build an AND gate. So you realize this is the truth table. How can we construct something like this? You say, okay, it should be doing this thing. This is the function of it. And then you realize, hey, I know how to make an inverter. I know how to make an AND gate. NAND gate's output inverted. I have an AND gate. hey, we are getting somewhere. You know, now this is 6 transistors. So if you put all of them together, here we have our NOT gate. We started very simple. Then we started with the NAND gate. We combined them, we came to the AND gate. And this is the way we are building. And now you're also getting the idea. All of these transistors, if you look at it, they are all like the same thing. They just work as switches. We combine them in different sort of combinations. We connect their inputs, their outputs together, and we grow the functionality as we grow up. There are some generic rules of how they can be constructed, and let's just talk about this for a few seconds so that we are clear on this. All such gates can be constructed in a way that we have one network built out of PMOS gates that pull things up, and we have one network built out of NMOS gates, NMOS transistors that pull the output down, and we apply inputs. If we are constructing, we can quickly construct actually any given logic function into this network, and there are rules that allow us from one network go to the other one. You want an example? Who wants an example? Okay, so let's construct it's a very simple, silly example. Let's start with one. So, who wants to, someone dictate something? Who's a volunteer? Nobody? Yeah. A and B or C? That's it. Plus D. Okay, so here's the rule. You start with the NMOS part, okay? And A and B. So A has to be here, and then B has to be here, right? They are in series, NMOS. And then or C, or D. Ta-da! So this is the NMOS part. So this means actually, if you look at it carefully, if A and B is 1, the output will go to 0. If C is 1, the output will go to 0. If D is 1, output will go to 0. Well, it's not really this function we are doing, it's actually this function, right? I'm cheating. Well, if I don't want this, what can I do to get the real function? I hear an inverter, yes. Ha! We did the N part. On the slides, there is the N part. How do we do the PMOS part now? We have to rearrange them in a way that while these guys are pulling it down, nothing should pull it up. And the rule is very simple. Everything that you see in series should become in parallel, and everything that is in parallel should become in series. So we have like 1, 2, 3 things in parallel, so these will be in series. So let's start. We have this guy here. This was in series, so let's have them in parallel, A, B. Now this guy comes, oops. This is C. And then this guy comes, D, and this is the supply voltage. There you go. 1, 2, 3, 4, 5, 6, 7, 8 transistors plus 2, 10 transistors, and we have the Y equals to A, B plus C plus D function if these are A, B, C, and D. Convinced? No. Okay, let's at least argue with the fact that I have here a part that is the NMOS, and here I have a part that is the PMOS, and somehow looking at the function, I was able to derive how these things are connected, and once I have this, I was able to calculate somehow magically, okay? Help. No? It's really scary. I don't know if it's yes or no. Who says it's okay-ish? Excellent. I'll take okay. Frank, what did you do? Okay. So, foolishly enough, I was trying to give an example, but we have the same thing here. So there's a pull-down network and there's a pull-up network here. And we also discussed that whenever you want to pull these things up, the PMOS transistors, out of the way they are constructed, are more efficient for pulling it up, and the NMOS transistors are better for pulling it down. So there is now one question, and as an engineer, you should always try to do this thing. Don't listen to authority, right? I mean, say, yeah, construct them. So what happens if they both pull up and down at the same time? Yeah? Yeah, it could be. What happens in a short circuit? Okay. Well, you know, those transistors, there could be a stronger transistor and there could be a weaker transistor. So the bigger one, if says, you are coming this way, and the other guy says, no, you're not, you know, then you're going this way. If they are both the same, there might be too much current flowing. Instead of actually doing the logical function, you might end up somewhere in between. It's not something you want to do. It's not helping you realize your function. So this is one of the ideas. It is possible to, notice that it says likely incorrect operation, right? So it's not guaranteed that things will completely break down. It's not healthy. And it could really break down, or it could be really unpredictable. We also don't want that nobody pulls this thing up and down. It would be like this poor output is an orphan. It's like I'm whether 0 or 1, I'm floating, maybe shall I be 0 and 1? And this will be a problem when you're building circuits, because such floating outputs actually will create problems for the next stage, because the output of one logic gate will become the input of the next logic gate. And if you remember, we were talking about if A is 1, B is 1. So now, if A is like 0.45 or whatever, these calculations that we made will no longer work the way they want. So we want to avoid both cases. We don't want both at the same time transistors pulling up and down at the same time. We also don't want to have the option where the output is not being actively driven. Okay. So usually these lectures are horrible because we are telling you lies continuously, right? And we said most transistors are switches. You can switch them on and off. Well, yes, they are switches, but they are not perfect switches. They are sort of adequate switches under the right circumstances. For example, when you look at this structure, you could argue, why do you always put PMOSs at the top? You say, yeah, well, you know, PMOS transistors work very well when they pass a 1, but not so good when they do zeros. So they are switches, but they are kind of better for, you know, transferring one kind of information. And so this is the result why we end up with, you know, insisting that we put all the PMOSs on top. The details, we are not going to discuss it here, but in your lecture, in the books, you can actually read a bit more about why this is the case if you're interested. Now, speed. Which one is faster? What happens if I put transistors in series? What happens if I make them larger? There are all kinds of things that contribute to it. Remember, I was talking about the current here, about the sizes of the transistors. I said, hey, if this transistor is wider, the current will be more. If it's twice as wide, there will be twice as much current. Well, current is what makes the transistor switch, the next transistor switch its state. The more current you have, the faster the transistor operates. Now, if you put things in series, you will, if you just mentally try to do this, you'll realize current flows through one and then flows through another one. It's like when you put them in series, there is like resistance going through both of them. So the transistors in series become slower. Whereas if you put transistors in parallel, it is like, okay, current is flowing through this transistor, and in parallel there is a second one. It is as if the width of the transistor is doubled, because it not only goes through this one, it also goes through the other one. So there is a way, or there are some electrical properties which depend on how you connect them. Once again, the series connections are slower than parallel connections. And what can we do about this? You can read more in your books, because we are not going to go into the details of what is happening here. Now, there is one more thing that we need to briefly talk about. And these days, this is one of the most important things. When I started electronics, we were all concerned about the speed. And the speed more or less boiled down to this thing. I mean, how much current? Assume that higher current, faster circuit. Then the other part was the area. We were looking at how much surface area we needed to make one transistor, because they told us how large my circuit has to be if I need to put 1 million transistors. You know, it will be the size of this building, right, if I'm drawing it this size. And only later on, in like 95, 96, 97, people realized that the power consumption is an issue. The first chip was an Alpha 2164. That guy was consuming 80 watts. It's forbidden now, but there's something called a light bulb, and light bulbs were like 80 watts. They were illuminating an entire room. And it's a small chip, about the size of this size, 2 by 3 centimeters, and it was giving off 80 watts of heat. You can boil water on it. I mean, you can make steaks on this. It's not like, it's a little bit warm. No, it's like searing hot. So that was the first time when people said, okay, putting like a billion transistors is maybe not a good idea. We have to think about it. And soon they realized that the power consumption has two parts. The first part is what we call the dynamic part. And the dynamic part depends on the square of the supply voltage. Remember, we were talking about 3 volts. I say it's between 0, 3, whatever. So that voltage, the frequency, how fast we operate the circuit. So a circuit operating at 2 gigahertz consumes 2 times more power than, if everything else is equal, if you run it at 2 gigahertz, it's twice as much dynamic power. The capacitance, well, that depends on the structure of the circuit. It's all the wires and everything, and all the transistors and the gates add to the capacitance of the circuit. So you are switching them from 1 to 0, meaning that you are charging and discharging capacitances, and this is where you are losing the power. Now, this has had a profound effect of how we were designing circuits. What is the best thing to do if you want to reduce this? What would you do? Yeah? Lower the voltage. Why? Because it's the square of the voltage. So dropping the voltage by, factor of 2 drops the power consumption, the dynamic power consumption, by a factor of 4. Yay! Right? Let's make it 0. Then power is 0. It is true. So there is a minimum voltage we cannot go indefinitely down, but this is also the reason why we ended up reducing these things. Well, we can lower the frequency or we can lower the activity, but this is the things that we've been all fighting about, and if you go and try to do modern architectures, this is one of the more important things. The second part is the static power consumption. This is again the same voltage, and every transistor, those ideal switches, well, those ideal switches are not so ideal. There is, the current is supposed to stay here and not go anywhere. But current is going, electrons are dropping left and right. It's like when we have this class, at the beginning, we have 400 people visiting us. Towards the end, we'll have like a small select group who have nothing better to do on a Friday afternoon to come and visit us. So, there will be leaking effects and things will go away. And the problem is you combine them by 1 billion, and that makes a lot of power. So we end up discussing these things. It's not always power. Sometimes we are more interested in energy consumption, especially if you are looking at a battery-operated device. It's actually how much work you do with the power. So it's power times time gives you the energy, and your battery contains a certain amount of joules, certain amount of energy, and you are concerned about how much can I do with this amount of energy. Because reducing the power, well, you can make it zero, but you are also not doing anything. So you also want to balance these things out. So if you want to read more about this, we have also a chapter in Harris & Harris. Just as a summary, we looked at these gates. So we had the inverter. I didn't show this to you, but you can imagine how can I make a buffer? Well, the input is 0, the output is 0, the input is 1, the output is 1. Some of you will say, just draw a line, no transistors needed. Or you can take two inverters, invert it twice, you will get the same function. It's funny, but this is how you do it, actually. The AND and NAND gate, we looked at it. But similarly, we can construct also these simple logic gates by combining the transistors accordingly. So I was attempting to do a horrible attempt there to put them together. We can also make gates more than 2 inputs. So this was my attempt at making a gate with 4 inputs, A, B, C, and D. And you can actually go crazy, and you can, 3-input AND gate doesn't look crazy, but you can make a 10-input NOR gate out of transistors. Why not? You can read more about this thing. So we need to talk about these transistors now, because there is this Moore's law. Who has heard of Moore's law? Who has violated Moore's law? Who was ever arrested because of violating Moore's law? So Gordon Moore was founder of Intel, and he was very bored in one meeting, and he was doodling. And then he ended up making this graph. This is actually from his original paper. And he realized that, hey, in 1959, we made the first transistor. In 1962, we actually managed to make 3 transistors on a chip. And then 1966, this is where he stopped. And then, this is log 2. So he said, yeah, we are making about 60, 65 transistors now. And then he says, oh, look, this seems to be a straight line. Let me just go straight up. And then he says, in 1975, 2 to the 16, so we'll have 65,000 transistors. And, it's a good day of work for Gordon Moore, because he's sitting in this, investors meeting, and he's doodling and things like that. Actually, then he had like the cost of components. So it goes down, and then all of a sudden, because of technology, the yield becomes problematic. Putting more transistors becomes more expensive. So it's a bit more complex than this. But then he says, in 1970, the unit cost is going to go down, so we are going to continue like this. And in effect, this is kind of what happened. So here you have the transistor counts. 4004 is the first commercial Intel processor from 1971. It had about 2,300 transistors. You could, if you really wanted, you could name them individually. Like every one of you could give 4 names, and then we would have the 4004. And now, not now, 2011, 10-core Xeon Westmer has 2.6 billion transistors, and it falls into this line. The exact definition, first of all, let's agree on one thing. It's not a law, okay? There is no court that you break it or something. It's more what we call a self-fulfilling prophecy. It guides the industry and says, hey, in the year 2020, I want to have so many transistors. Make it happen. And then there are some poor material scientists and engineers who are saying, I have to make a 20 billion transistor chip. And somehow they manage it. But it also tells us, it guides the industry, so you kind of know what to expect, which is very interesting. And so this is what the numbers look like, and this is what he predicted, so it looks good. This is really nice. The data visualization from ourworld.org. You can go and find this and visualize it as you want. They have the dates, and you can convince yourself that this actually fits. And you can go back to 1965 and you can find this paper. It's only 3 pages, and it is the one that, every electronic computer science architecture paper starts with Moore's law, blah, 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 blah. And it's just 3 pages, so it's fun to look into it. And, this is what he said. In 1975, economics may dictate squeezing as many as 65,000 components, which was like, oh my God, what is this guy saying? And but he was also concerned that will it be possible to remove the heat generated by tens of thousands of components in a single silicon chip? This is actually amazing if you think about it. 1965, before we start, I was telling you, the first time that we really said, wow, WTF, what is happening here, was like 1995, 96. 80 watts a chip, are you kidding me? I mean, it wasn't like, it wasn't a surprise, actually. So how do we keep Moore's law? Because at some point, if you're ever a fan of mathematical theories, you will say, hey, this cannot go on forever. At some point, you'll have to put more transistors than there are atoms and that kind of things. So we managed to manufacture smaller transistors and structures. So what do I mean by manufacture smaller transistors? This is why I drew it here. So when you talk about technologies, you usually refer to the smallest thing you can manufacture. When you talk about a 7 nanometer technology, it means that this dimension, the length of the gate, for example, is 7 nanometers. That's a tiny, tiny, tiny thing. And if you can make these dimensions go smaller, then you can put into the same chip, into the same area, more transistors. This is the basic premise of how do I do this? Well, remember how I was making I'll just put some phosphor here, some boron here, oxide, this. The moment these things start getting smaller and smaller, I need to get more and more creative. And there is a lot of material science coming in there. Some of these structures are already discretely countable. The smallest ones are here, for example, the oxide thickness is a few atoms, tens of atoms thick. And we try to develop materials with better properties. This is the fun part. If you ever end up in a place where they talk about new materials, take a periodic table with you and you can play bingo. Because all of those strange materials will come there. My favorite was, this isn't so interesting. We used to have aluminum as our conductor. Oh, I don't even have it here. There is aluminum, and we moved to copper. We are not using silver. Silver would have been perfect. The problem is, it's not only the materials, it's how they come and combine together. Silver is a mess. Silver wants to react with everything. Silver doesn't stay at this point. Silver says, oh, oxide, yoo-hoo, let's make acid, Whereas gold is like one of the nicest materials. It's like, I'm gold, I don't touch anything. No oxygen, nothing, I'll stay there. And so it's also how these materials interact with each other. What is that? There you go, hafnium oxide. We had air, we actually started with silicon dioxide. Why? Because the bottom material was silicon. To get silicon dioxide out of silicon is very simple. You rust silicon. You literally rust silicon, You heat silicon to 1,000 degrees, you introduce some oxygen, and that oxygen combines with the silicon, forms silicon dioxide. And you can control this process very, very finely and say, I'll cook this in, 1,052 degrees for, 42 minutes, and I'll have, 42 nanometers of oxide nicely produced here. But you want to, find a better oxide, better qualities. You start with air gaps. You start with hafnium oxide. use air for insulators. What does it mean? I mean, instead of putting a material here, you have to dig a hole that is filled with air and nothing else. They do this. But yeah, crazy. So stay away from these things. I told you that we want to manufacture these things, and some of these structures are 7 nanometers wide. 7 nanometers maybe doesn't mean so much to you, but we use usually optical processes for it. So you define how the structure looks like. There's a mask, there's some light, there's some lenses, and it shines on there. Now, visible light ends at around 300 nanometers. Ultraviolet light is 193 nanometers. So that's the light I'm using, and I'm defining a structure which is 7 nanometer wide. 193, 7. It's crazy, but still is, you can still use this to pattern things up to 20 nanometer and below. And you have to develop new technologies to keep on working with these. Okay, now that we realize, okay, there will be a way to make better transistors. Out of transistors, we can make gates. So we have now a way of building these simple things. Can we now build larger logic circuits? So we have to understand what is the basic logic gate. And we want to combine them somehow together so that we have something useful. Because, you know, for all the love of things, what is this thing? You know, like... I mean, this doesn't look like anything that you want to build, right? I mean, seriously. It maybe excites an electrical engineer, but for you, you say, hey, I want to build this computer. It is more structured. You have something in your mind. And so we need a way not to do it like ad hoc way, like looking at it and reasoning about it, drawing diagrams. We want to have a structured way of doing these things. So we look at, we say we can build circuits out of these gates. We can combine them together to realize any function that we want to have. And you say, okay, we will have a logic circuit, and it will have some inputs and some outputs, and I'm going to define what is going to happen inside. I'm going to give it a functional specification. I'm going to say, if these inputs are like this, the output should be like that. You're describing it somehow. That's the first thing. The second thing, after I've done with the functionality, maybe I'll also try to say something like how fast this should happen. For example, you know, add these two numbers and please finish it in a day or two. Okay, that's a timing specification. I lost completely the class. Okay, so we talked about that we have different types of logic circuits. So the combinational circuits is the one that we are talking about. They are beautiful. They don't carry a grudge, if you want. You apply inputs. The moment the inputs are applied, you have a specification that tells you what the outputs are. Memoryless, effortless. They are strictly dependent on the combination of input values that are being applied to the circuit right now. The name combinational or combinatorial is actually the same. It's not even a British, American English kind of thing. In some of the books, you will see combinatorial or combinational logic. They are both the same. Now, cherish the moments that we are dealing with these memoryless circuits, because the rules are very good. You apply inputs, the outputs are there. The other ones have a grudge. You know, you come and you say, here, your input is 21 and 42. And then the circuit is like, but yesterday you told me it's 35. Forget yesterday. Like, you know, this is, well, these circuits are, whatever you apply to it, you get it right now. So this is really nice. Later, in the second part of next week or the following week, we will see sequential logics, which has structures in it to keep the history of what has happened before. So it can remember what has happened. And then the outputs are not determined by the current inputs, but by previous historical, anything that you have told it, it will remember. And, you know, say, I remember. There is no going back from this. Okay, so what we want to do now is to be able to reason and think about and come up with circuits any kind of circuit that does this. And when I say any, anything required to build digital circuits will be possible to do this. Now, for this, we are going to use the Boolean definitions, the Boolean algebra, and it will look something like this. So we are going to say, hey, I have a set of inputs, I have a set of outputs. For every output, for example, I have S and C out. And for S, I say I have a function of A, B, and C in. I have a second function that determines the second output. And then somehow we are going to write this, at the moment, strange-looking, mysterious things. A and B, or A and C in, or B and C in. And we already know that we have a couple of logic gates that we reasoned about. So we have the simple NOT gate. We have the simple AND gate, A and B. So the result is 1 if A and B are both 1. And while I'm talking about it, you should remember this is a separate field than what I was just talking the previous hour. In the previous hour, we were able to build out of these transistors things that realize them. Now we are just reasoning about them. So we have the AND gate. We also have the OR gate. And you can imagine if this is like a multiplication operation, this is like an addition operation. So it's A or B. And the result is 1 if either A or B is 1. Now, completely independent of whatever was happening with the transistors, years ago, George Boole, 1847, started analyzing and devising an algebra just out of ones and zeros. The normal algebra that we use is a decimal system, has 10, we have 10 digits. But then why do you have to be limited by 10 digits? Babylonians use 60. Some other people use other numbers. So why not only 2? And his interest, as a mathematician, was ones and zeros. And he defined basic operations, addition, multiplication, and inversion, and said, hey, can I do any kind of definition, can I prove theorems, can I have an algebra that only depends on these? And thanks to his work, 100 years before anybody was attempting to build any gates, there was a mathematical foundation of how you can reason about it. It's actually very interesting because without this, you had a bunch of transistors and you had to say, okay, I have one, now I can put a billion, somehow I can combine them. Remember, I was reasoning and trying to tell you I somehow put them together. And so this is what he came up with, Boolean algebra. You start with some axioms. You just assume these things to be true. You say, let's assume these are true. And then you can derive first some laws and theorems. And that will allow you to manipulate these expressions. And the manipulation can also lead to simplification. You can have a very complex-looking thing, and by playing around with it, being smart about it, you can reduce it. Why do you care? Because we realize that every kind of these operations will end up being physically realized by a number of these transistors. The fewer transistors I have to do the same job, the smarter we are. It's better, I can do more in the same area if I can be just smart and reduce it so that I do not use so many transistors to do exactly the same job. And the algebra helps us derive these things, and it can also help us derive more sophisticated properties. So to end the lecture, I'm just going to go through the basic axioms. We don't have time to go through all of them, but let's just start with these simple things. And they are very boring, Like B contains at least 2 elements, 0 and 1, such that 0 is not equal to 1. And here, this is a nice English version. It's just a formality. You define 2 different operations. You can say, yeah, I have 2 elements. If I add them, I'm still an element of B, meaning that I still have a 0 and 1. If I multiply them, I have 0 and 1. Then comes the commutative laws. And you say, You know, A plus B equals to B plus A, or A and B equals to B and A. Yee-hoo. Now, it becomes a little bit more interesting. You can define for each kind of operation, you define an identity operation. You can say, hey, if I add 0 to any value, I get the same thing. If I multiply anything with 1, I get the same value. Then you have distributive laws. If you have two operations, A plus B and C, you can open this as A plus B and A plus C. Okay. And the complement, saying that, hey, if I take my value, complement it and add it together, I get my identity element. Okay. And there is also an observation that you have these two operations, AND, OR, multiply, add, and you realize that all the axioms that you can think of come in dual form. So anything that you have in one expression is also true for its dual. So you can take one of the operations. So if you see one of these axioms, you can take every AND operation. You can replace every AND operation with an OR operation, or every OR operation with an AND. Every constant 1 with a constant 0, every constant 0 with a constant 1, but don't change any of the literals, and everything is still the same. So if you say A and B or C equals to this, you can directly flip them over, and the thing still holds. So the next in your slides, I mean, we are almost running out of time, so I'll just show you a few. So this is the first law, and this is the dual law. So you see x plus 0 is x. The dual of it is x and 0 is replaced by 1. The result is still x. So next lecture, we will continue from the end of these laws. You can see that you can use them for proving algorithms, and we will continue with using Boolean equations to represent a logic circuit. I wish you a very nice weekend. Thank you.